Okay, hello everyone. Welcome back to Introduction to Elementary Linear Algebra with me, Gustina Elvianti. So in this lecture, we will explore the concept of partition matrices and how this concept can be used to simplify complex matrix operations. A partition matrix, or also called block matrix, is a matrix that is divided into smaller submatrices called blocks or partitions. This is useful for simplifying calculations, especially in linear algebra and computational applications. Here as example of partition matrix, we have A be a 3×4 matrix. We can partition A into its column vector, say C1, C2, C3, and C4. Or we also can partition into its row vectors, say R1, R2, and R3. And we also can partition into 4 submatrices called A11, A22, A21, and it's supposed to be A12, A21, and A22. For instance, we have A1 is A11, A12, A21, and A22. And A12 is A13, A14, A23, and A24. And A21 is A31 and A32. And A22 is A31 and A34. One of example of application of matrix partitions here is in scheduling a class. Let's say the secretary of the mathematics study program needs to manage class schedule for 4 cohorts of students, let's say first year to fourth year students. The schedule can be represented as a partition matrix where each block represents a different cohort. The schedule matrix S can be structured as follows. S is a matrix where entries is S1, S2, S3, and S4, where S1 represents the course schedule for the first year, S2 schedule for the second year, S3 schedule for the third year, and S4 is scheduled for the fourth year students. When dealing with large matrices, performing direct multiplications can be computationally expensive. To simplify calculations, we use block matrix multiplications, which allow us to treat some matrices as a single element and perform multiplication in a structured way. By partitioning a matrix into smaller blocks or submatrices, we can apply the same multiplication rule used for standard matrices. This approach is particularly useful in parallel computing, where different blocks can be computed simultaneously, solving large system of equations, where breaking the matrix into blocks makes computation manageable, or in image processing, where large pixel matrices can be manipulated efficiently. Here as an example, let's say we have A 2×3 matrix, then we partition it into A11 and A12, where A11 is the first and the second column of A, and A12 is the third column of A. And we also have B 3×4 matrix, and we partition into 4 blocks, say B11, B12, B21, and B22. where B11 is this one, and B12 this one, B21 is this one, and B22 is 2. So we can write the product of AB. We rewrite A as 8 partitions and B also. So we can multiply as if like multiplication of matrix. So we multiply A11 with B11, and then we add with the product of A12 with B21. And on the second column, we have the product of A11 with B21 plus A12 B22. Note that we have A11 B11 plus A12 B21 is, so this one is A11, this one is B22, and this one is A12, this one is B21, and we get this matrix. And also we have this one is A11, this one is B12, and this one is A12, this one is B22, and we get this. So let me recall again. We get this one for A11 B11 plus A12 B21, and this matrix for A11 B12 plus A12 B22. So we have the product of AB is this matrix, and the result is this. So the first to the third column of AB, and this becomes the fourth column of AB. Partitioning a matrix by rows or column is useful when we only need to compute specific rows or columns of the resulting product, rather than performing full matrix multiplication. This technique saves time and computational effort. Let's say we have A is M by R matrix and B is R by N matrix. We can compute the product of AB column by column. So we write AB as A, so we write B in its vector columns. So the product of AB is this matrix, where each column of the product is the product of A with the column of B. Or we also can compute AB by row. So we can write A as by its row, and B, and the result is this matrix. So we get the product of AB is the jth row of AB is the multiplication of the jth row of A multiplied by B. As we can see that here. So the formula states that the jth column of AB is the product of A with the jth column of B, and the ith row of AB is the product of the ith row of A with B. Here an example, let's say we have A and B like this. Then the third column of product of AB is we multiply A with the third column of B. So we get this one. And second example, the second row of the product of AB is the multiplication of the second row of A with B. So we get this one. Now we see matrix product as linear combination. Matrix multiplication is not just a mechanical operation. It has a deeper meaning in terms of linear combinations. This perspective is useful in many applications, such as solving system of linear equations, where solutions can be written as linear combination of basis vectors, transformation in computer graphics, where points are transformed using weighted sums of basis vectors, in machine learning, where feature transformations are represented as matrix operations. Now we see the formal definitions. If A1, A2 to AR are matrices of the same size, and if C1, C2 to CR are scalars, then the expression form C1, A1 plus C2, A2 plus blah, blah, blah plus CR, AR is called a linear combination of A1, A2 to AR with coefficients C1, C2 to CR. To see how matrix products can be viewed as linear combinations, let A be m by n matrix and X be n by 1 column vector. Say we have A like this and X like this. Then the multiplication of A and X, we can write like this. It is a matrix of m by 1. And we can write the multiplication as the linear combination of the column vector of A. For example, let's say we have A, this one, and this one is X. So the product of A and X can be written as the following linear combination of column vectors. So the product of this one is 2 times of the first column of A plus minus 1 of the second column of A plus 3 times of the third column of A. So we got the multiplication of A and X is this matrix. Now we see the product of AB where both of AB are matrices. Let's say we have A like this and B like this. Recall that the jth column of vector A of product of AB can be expressed as linear combination of the vector of A, in which the coefficient in the linear combinations are the entries from the jth column of B. So we can see that the first column of AB is the linear combination of the column in A, where the coefficient is the entries in the column of B. So this vector is, we can get it from 4 times of 1, 2 plus 0 times the second row of the second column of A plus 2 times of the third column of B. And also for the second column of AB, we can get it from 1 times of the first column of AB plus minus 1 of the second column of AB plus 7 times the third column of AB. I'm sorry, this is still typo. Now we see an application of matrix product as a linear combination. A real-life example of this concept is calculating the total cost of products based on different price categories and quantities sold in a retail store. For example, let's say a supermarket sells 3 types of products: fruits, vegetables, and dairy. These products are sold in different branches of the store located in 3 different cities. Let's say city A, city B, and city C. We define the following matrices. First, price matrix. We denote it as P, where each product has a different price per unit in each city. So let's say we have P like this, where the row of P represents the different cities. I'm sorry, this typo. And the column represents product of categories. And then we also have quantity sold matrix. We denote it as key. The number of units sold in each city for each product is recorded in this matrix. So it means that 100 units of fruits, 200 units of vegetable, and 150 units of dairy were sold. The total revenue of each city is computed as, let's say we denote it as R, so R we get from the product of P and Q. So we get this is P and this is Q. So the product we can write as a linear combination of the column vector of P, where the coefficient is the entries of the Q. So we can write the product of PQ as 100 of the first column of P plus 200 the second column of P plus 150 of the third column of P. So we get the revenue is this one. So the resulting revenue matrix R represents the total revenue from all products in each city. City A, $2,200. City B, 1,300, and city C, 3,500. Now we see column row expansion. Partitioning matrix provides another way to view matrix multiplications. Suppose matrix we have A is a M by R matrix and B is R by N matrix, and both are partitioned as follow. We partition A into its column vectors, and we partition B into its row vectors. Then the product of AB can be written as just like we multiply A with B. So the product of AB is A1 B1 plus A2 B2 and so on plus AR BR. Sorry, it's supposed to be BR. We call this equation the column row expansion of AB. For example, let's say we have A and B like this. We can write the product as we multiply the first column of A with the first row of B plus the second column of A with the second row of B plus the third column of A with the third row of B. So we get this one. It's just like multiplication of matrix. And we get this result for the product of AB. Now we see matrix form of a linear system. Recall that matrix multiplication has important application to system of linear equation. Consider a system of m linear equation and in n variables. This one. Since two matrices are equal if and only if their corresponding entries are equal, we can replace M equation in system 2 by this single matrix equation. So we can replace with this matrix. The M by 1 matrix on the left side of this equation can be written as a product to give. This one, we can write it as multiplication of matrix, this matrix with this column vector. Let's say we denote it as A, this one as X, and this one as P. Then we can replace the system of linear equation by a single matrix expression, AX equal to B. The augmented of the SLE2 can we get by adjoining B to A as the last column. Thus, we have the augmented matrix is this one. Now we study about transpose of matrix. If A is M by N matrix, the transpose of A, denoted by A to the T, or like this, is defined to be N by M matrix obtained by interchanging its rows and columns. That is, the element in the ith row and the jth column of A become the element in the jth row and the ith column of A transpose. So if we have this one A and if we transpose it, we will get the result this one. But the row will become the first row become the first column, and also the second row become this second column, and the M row become the M column. Here, an example, let's say we have this matrix. So its transpose is this row become the column, the second row become the second column. Now we see an application of matrix transpose. The transpose of a matrix is widely used in various fields, including computer science, engineering, finance, and data science. For example, a grayscale image can be represented as a matrix. Let's say we have A. To rotate the image 90 degrees clockwise, we first transpose it, then we reverse each row to complete the 90-degree clockwise rotation. So first we transpose A to get A transpose, this one, and then we reverse each row to complete the 90-degree. So we get, so the A rotated is this matrix. Now we continue to trace of matrix. The trace of a square matrix is the sum of the diagonal elements. For n by n square matrix A, the trace of A, denoted by this one, is the sum of its diagonal. Now we see an example of applications. Let's say a city has 4 metro stations, A, B, C, and D. The connectivity between stations can be represented using an adjacency matrix where 1 means there is a direct metro connection between 2 stations. 0 means no direct connections. And the diagonal entries represent whether a station connects to itself or loop or terminal station. Let's say the adjacency matrix for the metro system is given by matrix A, this one. So it means there is a direct connection from A to A to B, B to A, B to C, C to B, D to C, D to D, and this is C to D. Using the trace, we get the trace of A is the sum of 1 plus 0 plus 0 plus 1. So it's 2. So it means that there are 2 stations with 12 loops, meaning 2 stations are terminal stations where trains either start or end. So it's the end of this section. Now you try to find or identify a real-world problem where you can apply the material above. Choose a problem from daily life, business, science, education, technology, and so on, where matrix partition, transpose, and trace of a matrix can be applied. Okay, here is the end of this section. See you and have a nice day.